Hello and welcome to this lecture on project scheduling. Project scheduling is a complex undertaking involving a number of related steps, and it's easy to get lost or confused by the size and the scope of project planning and monitoring and controlling the execution of the project plan. But the good news is a schedule, and a properly defined schedule, will help you stay on task, do a good job managing what you're doing, and making sure you're focusing on the key achievable project goals and not getting lost or distracted by things that are secondary of importance. So let's kind of explain what we're talking about here. A project can be seen as a series of steps. One way of just looking at it is we do them all in order, and here we see, this is from our book of writing a research paper. Identifying a topic is considered to be step A in our project, and the researching the topic, drafting the paper, editing the paper. You have to give a presentation for this research paper, so that's E, and F is the final draft of the paper, and G is finishing up the presentation, and then you're done. That first example there is called a serial sequential because each item happens one after the other. And truth be told, once you are editing the paper and making your final draft of the paper, those steps are independent of creating your presentation and finalizing your presentation in PowerPoint or whatever presentation tool you're using. You might just be using cardboard handouts or something like that. So the second drawing here, we see that there are some parallel activities, and as you might guess, that creates, it's better from a schedule standpoint, but it creates a little bit of complication. So we have to deal with this slightly more complicated approach. So we're going to come up with a model for this called a network diagram. And AOA or an AON are two options for how we're going to represent our networks. An AOA stands for Activity on Arrow Network, where each arrow represents the task or activity that the node and the nodes link the arrows. So in this AOA drawing, which is in black on this screen, the activity B is joined to the activities C and D by the nodes between those arrows, and the labels are on the arrows. An AON for Activity on Node Network is what we're going to use in the rest of this presentation and what you see in the book. Here we use the nodes represent the activity, and the arrows link the nodes in the flow. So that's what we're going to use. When we're developing our activity network, we have a few rules that we can follow here. Again, remember, this is a complex process that can be confusing. By defining some rules and following those rules and trusting those rules, we can have a systematic way of having high confidence with our results. So first of all, you have to start off by determining in advance activity precedence. What has to be done before other things get done? We talked about things being done in serial, or things can be done in parallel. We want to find those activities. Regardless, every activity depends on something, if not multiple somethings. An activity cannot begin until all the preceding connected activities have been completed. So if you have to determine the topic of your research paper before you can write the research paper or start doing research, then that is a preceding element and it has to be done first. Arrows on networks indicate precedence and logical flow. The arrows can cross over each other, but it's better to draw them so that they don't. Network diagrams typically flow from left to right. They don't have to, but it's a nice consistent approach to make. It's kind of expected and common there. Each activity should have a unique identifier. It can be a letter, can be a number, can be some kind of a code, product code or something. We'll probably just use letters in our examples here. Looping, where you have the activity arrow looping back to a node that's already been used before, one of the circles that's already been used before. You're not allowed to do that. You can't have loops inside your activity node. And then finally, although it's not required, it's common to start with a single node and it's common to end with a single node. The notation that we're going to be using here is a little bit of a complex activity node. It's got a lot of information on it, but that information is going to be helpful to us. And the first time you look at this, it might seem a little bit overwhelming. There are 8 elements inside this diagram in the upper right. Early start, identifier number, and early finish across the top. In the middle, we've got something called the float, and then a descriptor of the activity, what this activity is. And then we have late start, activity duration, and late finish. Now the position doesn't have to be upper left, upper right, and so on, but inside the node you have to do those things. So you can see there's an example there. The research topic, we'll see all the things are there. The early start date is in there, 12/17/08. The identifier number is in there. The finish time is in there. Actually, it doesn't say early start and early finish in this case. It just has a start and finish. But that information is in there, the duration, the ID, which is the number 2, the research topic, which is the activity descriptor, and so on. So actually this diagram, we're supposed to be 2 sets of dates, early and late start and finish, and early start, early finish, late start, late finish. We'll see more about that in a second though. But the point is we're going to see this diagram in the upper right hand corner more in the future as we go through these. Some other quick terms, serial and concurrent activities we talked about in this diagram. B, D, and E are all serial. They go one after the other. I'm sorry. D, E, and F, there to the right, the last 3 are all serial. They go one after the other. B and C are concurrent activities. You can be working on B while you're working on C. They're concurrent. Successors and predecessors. Successors follow. So B and C have the same successor. D is the successor. And then E is the successor of D. Predecessors are things that come before it, right? So A comes before B and C come, there are 2 predecessors to D, and so on. Merge activities are where things join. D is a merge activity because B and C are merging into D. A burst activity is an activity that branches into more than one. So A is a burst activity because A has 2 successors. A path is following the arrows. So a path would either involve B or C, but not both. So it could be A, B, D, E, F, or it could be A, C, D, E, F going through the top or through the bottom, but a path does not include both B and C in this case. And the critical path is the path that we want to find out. That's where we want to focus our time, effort, and energy, our resources, because if the critical path gets a delay inside of it, it's going to throw off our final time at the end. So finding the critical path is one of the main things we're wanting to do here, and once we know that critical path, we can manage it. Now, one of the things we're going to be doing here is coming up with, we have to have time estimates, because those time estimates are going to be data that goes into our network that we then use to come up with start times and end times, and based on that we find critical paths and so on. So how do we find those times? And I'm not going to get too much into this. It's in your reading. They go into it a little more. It has to do with statistical analysis. On your quiz, probably not going to do a lot of this on the quiz, because certainly on a timed quiz, I don't want you to have to be doing a lot of math. But it's straightforward math. You could plug it in to a spreadsheet very easily to find out the times associated. So we would make these estimates. We make estimates based on past experience, which is a good way of getting an estimate, or an expert's opinion, which is an estimate, although an expert's going to do it faster than you and I are. So an expert's opinion for himself is different than perhaps a novice or a non-expert doing the same thing. And then there's a mathematical way of doing this where we say, okay, what's likely, what's if things go bad, if we have a lot of bad luck, how long is it going to take? If things go really great and everything comes through, we get an optimistic value. We can come up with 3 different values and do some mathematics, some statistics on those 3 values to come up with a single value that we then plug into our network to do our critical path determination. And the formulas for these are pretty simple. A is, and you can see the letters here, A is the optimistic, very, very short time. B is the pessimistic, very, very long time. And M is the middle, or most likely time that we're guessing. So variance is, I actually probably should have put these the other direction. Duration is how long we think it's going to take, and the variance is, the smaller the variance, the more likely that number is going to be correct. So just real quick here, we can see this math, and again, I don't think there's many test questions on this. And if they are, they'd be very easy math to work through. the variance and the durations. And those are the two formulas. And here we have a set of tasks, the predecessors for those tasks, which doesn't really matter for our calculations. The only thing that matters for our calculations is what's our low-end optimistic time, what's our middle or likely time, and what is our high-end, if everything goes wrong, Murphy's Law, we get a flat tire, everything, pessimistic time. And we can do the activity duration by just saying it's A plus 4 times the middle plus the pessimistic time, right? The optimistic plus the likely times 4 plus the pessimistic, all divided by 6. So basically we're weighing the most likely value much more heavily, 4 times more heavily than the optimistic and the pessimistic. And if you just do the math on those, we can say, so this first example with an optimistic of 7, a likely of 8, and a pessimistic of 15, 7 plus 8 plus 8 plus 8 plus 8 plus 15, I don't know why I said 16 there, it should be plus 15 divided by 6 equals 9. And you can double check that math, but I'm pretty sure that's right. I think I was supposed to have 15 there instead of 16. 13 plus 16 plus 16 plus 16 plus 16 plus 19 divided by 6 is a 16. And that makes sense because 13 and 19 are directly the same amount away from that middle value. So our middle most likely estimate is exactly what we get when we do our math here. And so on. 14 plus 18 plus 18 plus 18 plus 18 plus 22 divided by... I really made a lot of mistakes there. I wasn't copying my math over. I'll fix these now. Is 18 and so on. So we can come up with those. A very simple formula. The low time plus 4 times the middle time plus the high time. That gives me 6 values as a whole divided by 6. That gives me my average time. Now, how good is that estimate? The variance is telling us our how big is that standard deviation. In other words, no two instances are exactly the same, but the smaller the standard deviation, the closer they all kind of cluster together. And the higher the standard deviation, the more they separate out. If we were using target practice, a really excellent shot is going to hit, if he doesn't hit a bullseye, he's going to hit very near the bullseye, and all of the shots are going to be in the same area. That would be low variance. Somebody else might make an occasional dead-on bullseye, but the 10 shots only, 3 of them aren't even on the target, and they're all over the place on target. That would be a high variance. We can calculate the variance using a separate formula, which is the pessimistic minus the optimistic. How big of a variance is there? How big of a difference is there between the pessimistic and the optimistic? Divide that by 6 and square it. And that gives us some values. And again, you can just kind of see there on the screen. 15 minus 7, right? 15 is the pessimistic, 7 is the optimistic, so I could subtract those. That difference would be 8, sorry. 15 minus 7 is 8. 8 divided by 6 gives us a value. Square that value, and it's 1.78. A low variance, the lowest variance is this example right here, 0.04. And we can see that that's a low variance, 12, 14, 16. The optimistic and pessimistic are pretty close to the middle likely score. In fact, they're off by 2, and the likely is 14. It's almost barely a tenth off. This one has our greatest variance. We're expecting it to be a 4, but in a worst case scenario, we're more than 3 times that value, right? And the variance, the high variance value, is reflected there. So we come up with our numbers, we can do our math, and we can come up with some accuracy with those. The point is that once we get our numbers, we're going to simplify this. So table 3 shows us a project that we're working on where we're dealing with signing a contract and having a questionnaire, and then finding your target market audience here and doing a survey and creating a presentation and so on. And we can come up with numbers. We can come up with our estimates based on whatever estimating technique we're using, have our optimistic, our pessimistic, and our middle value, run the math on that, low plus 4 times middle plus high, divide that by 6, and I get a number. And I can see 12.7 and 5.8. I'm just going to round those to 13 and 6, as you can see. 4.2 rounds to 4, 9.3 rounds to 3, and the things that were integers stays integers. So now I've got integer value durations. These are approximations anyways, so rounding them to the nearest whole value isn't going to hurt us as we come up with our charts here, and it's going to make our numbers a lot easier to do as we work through them. So I've got my activities, I've got a description of those activities, I've got the predecessors on those activities, so I can build a chart based on my precedents. I can see some of these are burst activities and some of these are activities where the joint activities where it comes back together, and I can do my diagram. In fact, if I take that table 4 that we were just looking at and draw it out using the activity name, the activity identifier, the description, draw out the precedence charts. I can see, for example, that A doesn't have any precedence, so that's my first one. B has A as a precedence, but so does C. And in my diagram, both B and C have A as a precedence. B and C are the precedents for D, so both B and C join for D, and so on. So I can just draw this out, and associated with each one of these nodes is the estimated duration. 5 for A, 5 for B, 6 for C, 13 for D, and so on. Okay, great. So what are we going to do with this? We want to do some work on this network. We want to do some calculations on this network. And what we're going to do, you can say, oh, simple calculation, I can just look at this, and I can see that there are 4 paths through this, right? The red path, the orange path, the purple path, and the green path. I can see 4 ways of getting from A to H. And I can even add those values up, right? The red adds up to 18, and the green adds up to 29, and the purple adds up to 30 and 22. Great, so I'm done. Well, we can do more than this. That doesn't really help us. That doesn't tell us which of these nodes is the most critical node. Where do we need to be focusing on? Where do we have some slack resources? How can we do so? We can't really manage based on this, shooting from the hip approach to our project management, our project schedule. We really want to spend a little time analyzing this and find out where our critical paths are, and focusing on that critical path, we're going to have much, much better success. So let's figure out how to do a critical path. And that'll be pretty much the remainder of this lecture here. I'll say a few things after we get to critical path. First thing to do is do a forward pass. Work our way through the network from the start to the end using an additive or an accumulating approach. And I've got there in the upper left-hand corner, I've got that diagram with the 8 key pieces of information, and where they are spatially in our diagram is going to tell you what we're talking about. So the upper left-hand corner is the early start time for this project, the number of days, and the upper right is the early finish time, the number of days for this project. The first activity A, if you remember from our chart, it didn't have any predecessor, so its start date is 0, and it took 5 for a duration. So we add the duration to the start date. 0 plus 5 is 5. Now A leads to B and to C, so A finishes at 5, therefore 5 becomes a start time for B, and A leads to C, so the finish time for A becomes a start time for C. And I know the time for B is 5. 5 plus 5 is 10. I know the time for C is 6. 5 plus 6 gives me 11. So if it starts at 5, it'll end at 11 because it takes 6 days to complete. Now something interesting happens here at node D. I've got 2 preceding elements in my network, B and C, and they both have to be completed before D can be completed. That's what the diagram means, the way we've drawn them here. So what's the start time for D? Can I start it when B finishes, or do I have to wait for C to finish as well before I can start activity D? And if you think about it, they both have to finish. That's what the diagram means when they're joining together. So D's start time is the greater of all the nodes that lead into D. Same thing here with H. If we look at H, I can see that there's an option of E, which finishes at 16, F, which finishes at 28, and G, which finishes at 20. And all of those have to be finished before H can begin. So the larger value, 28, is the start time, the early start for the identifier H, the presentation. Okay. So simple rules there. We can make a forward pass of coming up and adding the duration to each one of those. And again, just notice the duration. It's real easy. The start time plus duration gives us the end time. Start time plus duration gives us end time. Start time plus duration gives us end time. So I know there's a lot. The first time you look at that, it's pretty complicated and busy, but it's not such a big deal. Okay, so now what do we do? So we've filled in all of our early starts and early finish times by making our forward pass. Now we want to work backwards to fill in all of our late start and late finish times. The backward pass is subtractive. Just like we added elements from 0 up to the end date, the backward pass, we start with the end time and subtract values to work backwards. So our project finish date was 30. We're going to let that be our late finish day as well and work backwards. And just like we used to add the activity duration, we're going to subtract the activity duration. So 30 minus 2 gives us 28. H is done. Now H had 3 predecessors, but working backwards, it's almost like a burst. So that 28 goes into the late finish time for E, for F, and for G. They all get a late finish time of 28. And in each case, late finish minus activity is late start. 28 minus 6 is 22, 28 minus 4 is 24, 28 minus 9 is 19. And I can work my way backwards. Now something interesting happens here. If I looked at D, and I don't have it drawn here, but the 24 would pass here, 24 here. My survey time for for this D was, I don't remember what it is. I have to look at the next slide. It was a 13, so 24 minus 13 gives me 11. What do I do in B, node B in this case? Because there are 2 nodes feeding into this in my backwards pass. I've got E, which has a late start time of 22, and I've got D, which has a late start time of 11, and both of those, E and D, feed into 22, feed into node B. So what is the value that goes into node B here? Well, it's a very simple rule that when you're doing a backwards pass and you have your your consolidation points are what was a burst. B was a burst moving to the right, so going backwards, we're joining into that burst. You always use the smallest of the late starts that are coming into that burst. So the smallest between 11 and 22 is an 11. Likewise, C has to choose between an 11 and a 19, and the smallest value for C is an 11. So 11 for B, 11 for C, 6 and 5, the smallest value is 5, so 5 is our value for A. We now have a complete network, or almost complete network. We now have a network that at least is complete through early start, early finish times from the forward pass, and late start, late finish times from the backward pass. What's next in filling this up, and the thing we haven't done yet, is this thing called the activity float. It's the only piece of information missing at this point. And the activity float is very simple. The float is also sometimes called the slack. It's how much buffer, you'll even hear people say sometimes, how much leeway there is in our schedule in certain places. And we calculate the float or the slack or the buffer for each activity node by simply noticing the difference between the late start time and the early start time. Right, the early start time is optimistic, we get to it really quickly. The late start time is, there's delays elsewhere in the network, well, we can still start it then. So we just subtract those. And I've circled 4 examples here to look at. In node B, early start is 5, late start is 6. The slack is the difference between those of 1. In node E, 22 and 10, the difference between those, the slack, the float, is 12. 11 and 11, when you have the same early start as you have the late start, and you always will have some of these, then the slack is going to be 0. 11 and 19, the difference is 8. We do that for every node in our network, and then our network is complete. At least it is in the sense that all the nodes in our network have all the data we're going to put in them. At this point, now that the network node is complete, we are ready to determine the critical path for this activity network. And the critical path, by definition, is the network path from start to finish where there's no slack. And I can look, starting at the beginning, there's no slack at the beginning, and there always will be no slack at the beginning. And then I can see that C, in this case, has no slack. And then C can go to D or G. D is the node that has no slack. and then F is the node that has no slack, and then H is the node that has no slack. So that path, A, C, D, F, H, that is our critical path. Those activities on the critical path, those are the activities that if they go a day or 2 or 3 long, then we miss our project deadline for a day or 2 or 3. Now, if I miss node B here by 1 day, that's okay. I actually have 1 day of slack built into that. I can miss G by 8 days. I could start this whole project a week late, as long as I spend some resources making sure that C and D and F are done on time. Because these are my critical paths. Missing these days is going to be a problem for us. Where I have slack, I now have this in my node. You remember when we had that diagram back before where we just had the 4 different paths and just ran through them? And I said it was poor for managing the project. You can see now that even though I have to make sure that all these things get done, B has to get done, and E has to get done, and G has to get done, I know that what's really critical, and when it comes down to 3 days left, 2 days left, 1 day left, we're about to be over time, I want to make sure that the items on the critical path are done on time so that I actually finish this project 30 days after I begin it. Just a couple more ideas here. 2 more quick ideas. First of all, this idea of laddering. Laddering is a way that we can take sequential projects, sequential steps, and actually speed up sequential steps. And you say, there's no way to speed up sequential steps. That's impossible. They're sequential. Right? I have to do A, then I have to do B, then I have to do C. And A takes 3 days, B takes 6 days, C takes 9 days. It's going to take me 3 plus 6 plus 9, which is 18 days to do these 3 activities. There's no way possible to do it faster. Well, if they're actually truly sequential, A before B, B before C. And I understand that, but some projects, even as you're finishing A, and it's still, you'll notice in this laddered version, A still takes 3 days. But I can break it into sub-steps. So A1, A2, A3, each one takes 1 day, so that gives me a total of 3 days, just like we had before. But once A1 is done, as the second sub-step, right, the second part of A is being worked on, I can also be doing B at that point. And B can be broken up into sub-steps. And C can be broken up into sub-steps. So some tasks can be broken up into sub-steps, and some tasks can't. If a task can be broken into sub-steps, then you have the opportunity to use laddering to allow you to gain efficiencies on sequential project steps. So this whole project, we add up all the numbers through here, we actually get done in 12 days instead of 18 days, so we have a significant 50% increase in our reduction in our time by doing that. One more little activity that can be done is this idea of hammocking. Especially as I have very large complex projects, and a tool like Microsoft Project is what you would want to use if you're managing a very large complex project. I'm going to have lots and lots and lots of nodes in my activity diagram, much more than the 10 or so nodes, 6, 7, 8, 9, 10 nodes we're looking at here. I might be doing 50 nodes or 100 nodes or 300 nodes in a project, and that can get kind of overwhelming at times. So to help create simplicity, what we can sometimes do is take nodes that are kind of related, especially if they have the same budget and the same management team behind them, and we can hammock those. We can kind of group them together and say, yeah, A leads to B leads to C, and the start time for A, best case is 0 to 5, and then 5:15, and 15:18, and so on. I can combine those into just, okay, there's this combined activity, this hammock. We're wrapping them up like you wrap something up inside of a hammock when you store it. And they're going to start at 0 and end at 18, and don't worry about the details. Right? It's almost a level of granularity where I'm not caring about that much detail right now. It's going to start at 0 and it's going to end at 18, and I can have those. I can have any number of these little hammocked or grouped wrapped nodes in my activity diagram that when that time comes, or when somebody at the appropriate level of management needs to unpack it, you can break it back up into its smaller details. But when you're looking at the big picture as a whole, you're just trying to get the executive overview, you don't have to get bogged down those details. It's just a way of abstracting, is almost the word I would use, but they call it hammocking. Okay? And the critical path is what we really care about, because delays in the critical path cause real delays in the final outcome of the project. So what are some things that you can do to further reduce your time? Because if you can reduce the time on your critical path, you're actually going to reduce your project's time. One thing you can do is you can eliminate tasks, or consider eliminating tasks on the critical path. Are these really necessary? Is there a way to do these, something else instead of doing, this particular activity? Do I have options? Is this required? Because if finishing sooner has an advantage, getting out to market. It's much better to be a first mover on a business project. It's much better to be first mover for a new innovative technology. If there's any way to get there sooner, then it's worth doing. So you have to look at every item on that critical path and say, is it really critical? It's critical in the diagram. Is it critical to the project? Can I remove it from the project and still be okay? If I can, it will decrease the time it takes for me to complete the project and get it to market and get advantage of why we're doing this. Obviously, we're doing this project because there's some advantage to it, and more than likely, the sooner we get done, the better. Increase the advantage. Convert serial to parallel. See when things actually can occur at the same time, instead of having to wait for the one project to finish. If you have to leave them serial, you can't make parallel, then say, well, can I at least break it into sub-steps? Are there elements within each step that maybe can have some hammocking going on, or some laddering going on there? Hammocking was more abstraction. Laddering is where we break it into sub-steps and get efficiencies there. Shorten the durations on the critical path task. That's kind of going back to what we said before. Is there anything I can eliminate from the critical path? Okay, I can't. What about the things that are on the critical path now? Are those times accurate? Is there any way to speed up the time? Maybe throwing a little more money at the project will get us a little faster results. Either adding human resources or just rewarding and paying for overtime or something like that. And when you're looking to shorten, some strategies, heuristics, rules of thumb are to look at the early tasks. They tend to be a little easier to, a little more specific in our knowledge, and sometimes easier to shorten up. As you get toward the end of the project, it's really hard to know what you're going to be dealing with, and it's better to, if you have to leave a little bit of leeway in there, you're probably going to need it at the end more than you are at the beginning. Longer tasks are candidates for shortening because it's a relatively less change. So if I've got 3 days dedicated to a specific task and I take 1 day out, that's cutting it in a third the amount of time I have dedicated there. If I have 10 days to a task dedicated and I cut 1 day out of that, then I'm only cutting it by 10%. So it's significantly less of a relative burden to shorten a long task by a day than it is to shorten a short task by a day. Easy tasks that are, can be done easily, are good candidates for being shortened. And then finally, one thing, sometimes it costs more money to get speed. Some things can be sped up at lower relative cost to other things. Some things, speeding up, yeah, I can speed it up, but I've really got to pay some big overtime, or I've really got to bring in, some equipment, some machinery that's very expensive as opposed to the machinery we're planning on using for that task or whatever. Other things, you can speed them up at a relatively lower cost, and those obviously would be good candidates as well. Okay, so very good. That is our project scheduling lecture, or at least part 1 of this. We're going to talk some more about this in the next lecture, next chapter.